was some few weeks ago asked if I would talk here something about what I'm doing, and well, I'm an undergraduate, so I'm quite the youngest one here, but I'm doing now research for my master's thesis, and my tutor is Maaret Korpi, and my master's thesis is about these elephant trunks, which the M16 Eagle Nebula pillars are quite good example. I thought I would put some elephants there too, so that there could be some comparison quite called elephant trunks. But anyway, research has just started about a month and a half ago, so there isn't actually a lot of code or results to show right now. I just thought what I'm going to do. Okay, for a little bit background, the elephant trunks, like you saw in that picture, are kind of small features that are located in 82 regions that are, well, basically those regions of industrial matter where the gas is highly ionized. It's mostly hydrogen, but some other elements as well. And the center of the region, there are usually some cluster of bright, very bright O1b spectral stars that cause the ionization. And there is also important star formation happening in these regions. I don't talk about this in detail here, but there are some quite familiar examples of major regions. Like I think everyone knows Orion Nebula, and that's one. There's also some of what I looked at, like Rosette Nebula and Eagle Nebula, and there's some good picture about some of major regions where you see this ionized bubble right here. And there is one elephant trunk actually. This wrench-shaped thing right here. So, for background still, a little bit about these elephant trunks. So, like you saw, there are quite those pillar-shaped clouds. They're usually they're on the edges of the extra region, so that at least the bubble, so that makes it somewhat different from so-called box globules, which are isolated. And so there is some. There are places where many stars are formed. There have been, especially quite a lot of research has been done about the Eagle Nebula, about this, and mostly the star formation is happening at the tips of these trunks of pillars, or whatever you want to call them. They are also, there is this quite new interesting observations that I'm trying to study a bit, that is made by, if I remember right, just the Gallman that found out that these elephant trunks are rotating somehow approximately like a rigid body. So, but just for example, the Eagle Nebula, as far as I know, this is very famous Hubble picture. At least, if I think about one Hubble picture, this comes to my mind even before I started doing research about this. It's about 2 kiloparsecs away in the region of constellation Sapphiros, and there's one the import Hubble observations where that pretty picture has come from is these Hubble observations that were presented in paper by Jeff Hester and a lot of other co-authors. Right here, it's quite comprehensive about the visual wavelengths of the Eagle Nebula. I think that this paper has, after this paper there was a lot of other papers about the observations, especially because they noticed these so-called evaporating gaseous globules, or EGs, that I think they are like these here, those small globules that, and they thought that maybe they were beds of star formation, but as far as I know, most of them aren't, but there is maybe about 15% that do contain star formation. Of course there might be more, but it's not possible to recognize. Like I mentioned before, the star formation happens mostly at the tips of fingers. So if this, well, this is a little bit about the background, but maybe a little bit more about what I'm actually doing. My interest started when there was this student seminar or something like that where I talked about this paper. So there is the most, I think, the most newest and up-to-date simulation about the formation of the elephant trunks that was done by me and some others, mostly about the formation of Eagle Nebula, but somehow, I don't know, it could be applied from almost any kind of elephant trunk situation. It's far as I know, is the newest simulation about this, and there are at least, the name of the paper was something, Trigger Star Formation in Bright Green Clouds, the Eagle Nebula Revisited. But there are some other two simulations, some by Williams in 2001, and Glenn White in 1999, and these papers are somewhat connected with each other because this was done first some numerical simulation about the subject, although this paper is mostly about the observations, and then the Williams paper commented on this, and then this paper commented on Williams et al. And there are a lot of same researchers with these two studies. So what did the simulation? I talk about this only shortly. It's the the simulation was so-called. It was only a hydrodynamical simulation. It's using some method called smoothed particle hydrodynamics, SPH. I don't know a lot about that method, so I don't think I can explain it to some person about that. But it's one of the most important things in the simulation that are important for us, what I'm doing now, is that they had this ionization feature that where there was the ionizing flux from these stars that caused the ionization. Oh, and it has had a great effect on the formation of the elephant trunk. Although there was also the same ionization feature, I think the Williamson thought, but it was 2D stimulation and so on, a little less complicated. The ionization actually caused shockwaves that in the end that did cause the tip of the cloud collapse and form stars. This is mostly the evolution, but there was this spherical cloud at first, where slowly the form begins to be more elongated, until in the end the core of the tip is collapsed. So at least when I'm finished with my own research, at least get something done, there should be something similar with my own simulations. But I'm not going to replicate this, but I'm thinking about adding some new features. Okay. One thing that I found interesting was that, well, there isn't magnetic field taken into account. There's only at the initial cloud there is this pressure there, where but there there was this normal thermodynamical pressure, but there was also this some kind of turbulent and magnetic pressures, and I think they got from some kind of observations the turbulent pressure, but the magnetic pressure, for example, was quite kind of like guessed. So okay, but anyway, this magnetic thing is back in India. What doing something like that?
Is that from their paper?
Yes, that's from their paper.
They got the plasma beta the wrong way around.
Oh.
Let us define something which is not the plasma beta.
Well, magnetic pressure over thermal pressure is one of the beta, right? Just a side remarks to confuse.
Yeah, that's canonical, sure. But that was just your definition of the beta, right? That's not in that paper, is it?
Oh, all these equations are from their paper. So
from your old paper, or what?
Yeah.
Okay.
Okay. I somehow get a feeling that I'm a bit confusion here, but anyway. They just calculated pressure like that. I don't. Right, but okay. So okay, I have to admit that my research is quite at the beginning. What I'm planning to do is to at least try to replicate this simulation using pencil code. But then I'm going to try to add a magnetic effects on this cloud, and also study if there is what might be maybe cause the rotation effect. Okay, this is what I am being able to do just right now has been mostly background research, doing reading a lot of papers, and I'm trying to get used to the pencil code because, well, I'm not still very familiar with it. I had one course about it in last autumn, but it's been taking a lot of time trying to understand the code more better, to do something on my own. And so it's been, at the beginning has been quite slow. And I have to notice that I have to program quite some new physics into the code. For example, the ionization feature, the ionization cost for radiation. I don't think that it exists in pencil code. So right now I'm concentrating on the ionization part, which is so that at least for the time being now. I started doing this about a week ago, and well, I was just reading about 5 lines of code just right about now, but they did talk. There was the ionization actually, but my paper used about these 2 equations where I think this is the radiation transfer and this is the ionization, actual ionization part. There is some irritating things about this too, because firstly I cannot find the reference where it is actually taken. So, and there is an example, this sigma, which is so-called ionization cross-section of hydrogen in the ground state, which I think means that it's the probability if the ionizing photon ionizes the hydrogen atom, but I'm still trying to figure out what the number they are using because they don't tell.
6.3 times 10 to the minus 18.
Okay.
So that's
not yet.
this factor is what makes the cloud dark, right? That's just opacity.
Yes.
The inverse of the opacity is the cross section, so therefore it's the same. But X is the ionization fraction, so if it's neutral, ionization fraction is, I mean, if it's ionized, then it's then X is equal to 1, and then it's opaque. Yes, it's only neutral. It's only opaque if it's
Neutral.
neutral. Yeah. That is an exact formula or approximation?
I mean
There's 1 minus
lower
X
one?
thing. Is that true? Correct for hydrogen, pure hydrogen?
Yeah. Unless you want to do level population.
Yeah.
And then you also need to take into account how the levels are populated.
And one thing
Very
that is
few
of course
people do that.
missing in this equation is where the light comes from, the source.
Sorry?
It's maybe so it's ETL formulation. It's ETL formulation for absorption. Because
Yeah.
there's no emission of the sun.
No.
Yeah, I mean it also the differential equation doesn't have the emission.
Yes.
Which, well,
But that would just come from a star, not from a distributed region.
you could have ionizing emission. Well, recombinations to the ground state produce photons that are can ionize again. So and they are produced within the ionized region itself. So that's an emission coefficient, which is often neglected.
Yes.
Because it's hard to deal with.
Yeah.
Okay. So in this case, one would simply say the radiation comes in from one side.
Yeah, it's come from outside in like a plane. So
Yes,
it's that kind of simple assumption.
it's very nice.
Yeah, but Like, like I said, I'm still trying to figure out this thing and seeing if they are good.
And in fact, so in fact, the factor that you have in front of the j in the second equation is exactly what you also call I in the equation above.
Yes. Yes. Yes.
So that's the ionization fraction. So whatever produces darkness produces at the same time new ions, electrons.
Yeah. Of course.
Well, the other way around, I guess.
Why?
I mean, so the ionization makes new electrons.
Yes, and therefore, and at the
But
same
how
time,
much?
it absorbs light.
Yes. Yeah.
So that's so the sigma n times 1 minus x is what I is,
Yeah.
which actually I have in front of me because I have the paper.
In fact, if I understand, the fraction of Q is what, in fact, is not absorbed. So
Yes,
that's it.
yes.
The same equation when you do experiment, when you have a target and you put photon on target and it absorbs the flux and you measure the opacity of the same equation.
So the one person who has actually implemented this is actually not paying attention at the moment. The only one person not paying attention is you. You have, I think you have basically implemented this, no?
Yeah, but not with radiative.
No, but I mean the rate. I mean you have the equation for the separate equation for
Yes.
neutrals and ions, and of course the d by dt is of course is really an advective derivative, right?
Yes.
So it is advective with the rest of the fluid, and of course it's also feeding by the magnetic field. So in that first equation there will also be a J cross B term in principle, because the Lorentz forces affect charged particles.
If you keep, then you have to keep track of the electrons in the.
Yes, and then there would be a friction term between.
But right now that's not an equation of motion, that's a rate equation. You're talking about an equation that should yet be there.
No, I think it's still the same equation. No, you have it is of course a rate equation, but of course so you have fluid which is moved around at the same time it's being produced and removed. So that's one and the same thing. It's a reaction diffusion equation, reaction diffusion advection equation.
But electrons aren't produced or removed by the Lorentz force or by...
No, but they are transported, affected.
Yes. But
They move, of course, not in a straight line anymore.
in this case, you have magnetic force.
So I think the equations make a lot of sense, and it would be completely natural to make sure they are in a equivalent form in the code. And if you're right, then Vladimir's part may actually work. Except that you'd introduced neutrals as opposed to ionized. I think we should do exactly the opposite.
Why is that then?
What? Because when people do ambipolar diffusion, for example, they normally rather think of the fluid, because the ionization degree is so small, they rather think of the fluid being mostly the neutral part. And so as far as the ordinary MHD equation is concerned that we have, they represent by and large the neutral part.
Yes.
And then there's just an additional correction for the ionized part,
Yes.
charged part.
Depends if